Now that we've understood a bit about the behavior that we're hoping to find from this, that there's something interesting going on, let's go through then our solution. Let's actually prove these claims now from a formal point of view. To do that, we have to now, of course, solve our time-dependent Schrödinger equation. And for that, we have to follow our step-by-step procedure. And step number one is actually, first, before we can do anything, we actually have to solve the time-independent Schrödinger equation. So let's write down that equation for this case. So in this case, that equation is going to look like minus h bar squared over 2m times two partial derivatives with respect to my state, right? And I'm not sure yet what label I will use. I'll have to see what kind of solutions I find. But that should then give me back then plus the potential, right? I'm not in free space anymore, times, again, my pure state wave function, has to give me back then the energy of this state times my pure state wave function back again. And again, as I said, later we'll come back once we understand these solutions and find some appropriate label or index for these pure states of energy. Now, to solve an equation like this, you guys know the general approach, or here's some general advice for solving any type of equation. When you're first faced with a new type of equation, the first thing you should do is kind of isolate on one side of the equation the most complicated term, and then put all the more easy to understand terms on the other side so you can focus on the hard parts of the equation. In this case, the most complicated part of the equation clearly is this second partial derivative. So let's solve for that. So the second partial derivative with respect to x of phi of x will equal then, well, let's see here. I have to put this term on the other side of my equation, and I can combine that then with e times phi. So I will get e minus v of x times phi of x. All right. And now, to finally isolate my second derivative, I'm going to have to clear this fraction onto the other side of my equation. So I have to multiply by its inverse, minus 2m over h bar squared, like so. So this is the type of equation that we will be solving. Now, one comment on this that I'd like to make is you will notice I have different behaviors, certainly in these two different regions, right? The potential has a different value in region 1 from the value it has in region 2. Region 1 and region 2 somehow have very different behaviors. One is classically allowed, the other is classically forbidden. So clearly the approach I want to do is to focus on this equation one region at a time. So first we will consider what goes on with this equation here in region 1. Next, we will consider what happens then in region 2. And finally, we will try to figure out what happens in this in-between region, right, where they join together, where the function is continuous but very sharply changing. And once we understand the behaviors in all three regions, then we will be able to understand the overall solutions. And then, having solved the time-independent Schrödinger equation, we can get back to our task of understanding the time-dependent behavior. And that's really what we will be taking up in the next lecture.